Good evening, everybody. Once again, you are welcome to another online review session. In today's session, we are going to use the questions from our chapter 5, end of chapter questions. I noticed that a lot of you have joined us. So before we get the session started, let me go ahead and acknowledge all of you. I see Freda Woods is with us, Area Waller with us, Ashley Intim Ade with us, Brianna Neal has joined us, Siobhan Cummings also joined us, Christopher Robinson II also with us, Gossin Adejumo with us also, Ines Kifando also joined us, Gine Jones also with us, Jaconda Kepas with us, Kiera Bradley, Lona Kuma, Maria Sankey, Mohammed, 22nd I see here, Oyin Oluskeye also with us, Pravin Cheka, Rudolph Brown, Shakira Hudson, Sandra Oyekere, Taylor Wright, and Valerie Prevail. All of you are welcome to today's session. Okay, we do have a lot of material to cover today, so let us go ahead and start right away. Ashley, can you go ahead and read this question for us? To here.
Okay. I can't really read, it's kind of small. It says assign R or S configuration to the chirality centers in the molecule. Blah.
Okay, very good. Yeah, you did very well. Okay, so the question is, assign R or S configuration to the chirality centers in the molecule below. And actually, we do have two molecules here. This is the first of the molecules that we need to assign the absolute configuration to the chirality center. Now, the question that I have for you before we get started, taking a look at this molecule here, of course, we know that the red is oxygen. Okay, so the gray is carbon. So here you have a carbon-oxygen double bond, and then you have attached to that you have a carbon-oxygen bond, which is oxygen also attached to hydrogen. So this here is a carboxyl group. Now, if I ask you here, how many chirality centers do you have in this molecule? How many chirality centers do you have in this molecule? One. Excellent. One. Okay, can you tell me where the chirality center is? Okay, one, okay, yes, that is correct. Okay, let me label the number, the carbon, and you tell me which carbon is the chirality center. Okay, supposing I say this is carbon 1, and this is carbon 2, and this is carbon 3. Where is the carbon? Okay, so, okay, carbon 2 is correct. Carbon 2 is the chirality center. Okay, so we are going to do this problem from my notebook. But before we do that, let me go to the other molecule. Okay, this is the other molecule we need to determine the absolute configuration. Okay, if I ask you how many chirality carbon do you have in this molecule? How many do you have in this molecule? Keep in mind that the blue is nitrogen, the yellow is sulfur. Okay, one. One is correct. That is excellent. Okay, now can you tell me where the chirality carbon is? Let me go ahead and number this. I will say this is carbon 1, carbon 2, and carbon 3. So where is the chirality center? Okay, carbon 2. Excellent. Okay, very good. So we are starting on a good footing right away. So let me go to my notebook. Okay, so this is the problem here. We have to determine the absolute configuration R or S for the chirality center. Now we all agree that this molecule only has one chirality center, and that is this one here. Okay? So now what you want to do here, when you are given a molecule like this, you want to position yourself. You want to position yourself so you will be able to see this molecule, the groups attached to the chirality center, so you will be able to see them in a three-dimensional orientation. In other words, you want to position yourself so you see some of the groups coming at you and some going away from you. So what I want to do now, I'm going to pretend that I am right here. Think of me as laying right here. Okay? This is my leg. And this here is my right hand. Think of this as my right hand. And this is my left hand. Okay, Ashley, are you trying to ask me a question? I'm getting some noise from you. Okay, so this is my left hand. And of course, this is my head right here. So I am laying down, facing down on this carbon here. So if therefore, the first thing you need to do therefore is to write this chirality center and all of the groups that are attached to it, write it out in a Fisher projection. So if you want to do that, what would the Fisher projection of this carbon look like? What would be on top of me? Let us say that is that carbon. What would be on top of me? So anybody has an idea? What would be on top of me? Methyl. Excellent. So the methyl will be on top. Notice what I've done here. I positioned myself so I could see this molecule in which two groups will be coming at me in an horizontal fashion, and therefore the other two groups will be going away from me in a vertical fashion. Keep in mind that we are dealing with sp3 carbon atom in which the carbon is sitting in the middle of a tetrahedron. Okay, so therefore, what would be to my left? What would be to my left? Okay, to my left will be exactly, very good. To my left will be the carboxyl group. Let me write it out in a better way. Actually, let me give myself more room here. Okay, let us say we have carbon is here, methyl is on top, and then here you have the carboxyl is on my left, and then below me, what is below me? What is below me? What is below? Hydrogen. Excellent. So hydrogen is below. Keep in mind we are writing this out in a Fisher projection. And then to my right will be this group here. This group here will be to my right. Okay? This very bulky group. That group doesn't mean too much to us. All we need to do is simply say that it is a big group. So let us represent that. We have this here. And then somewhere here we also have, so we have that group right here. Okay, now let us now go ahead and determine the absolute configuration of this chirality carbon. Let us start the make the priority assignment. What is priority A? Which group is priority A? Okay, which group is priority A? If we write it on the quiz like that, will you mark it correct? Okay, no, keep in mind, okay, the question is, if you write it on the quiz like that, will you mark it correct? Keep in mind the question they are asking you is to assign the absolute configuration, R or S. So what you want to do is to determine the absolute configuration and simply tell me whether this is R or S. So our focus is not on the structure. Okay, okay. So let us now do the assignment. Group A, group on right is A. Okay, that is not correct. Actually, the group on the left, the carboxyl is exactly. The group on the left is correct, which is the carboxyl. So that is A. Keep in mind that the carbon here is attached to oxygen, whereas the carbon here is attached to carbon. So oxygen has priority over carbon. That is why the carboxyl group is given the priority of A. Therefore, what is priority B? Okay, what is priority B? Of course, we know this. What is B? The group on the right, exactly. So that is B. Now, what is C? Therefore, C is exactly C. And what is D? Of course, D is this here. So therefore, at this point, we want to make our motion. We make our motion from A to B to C. We go through B to get to C. Ignore group D. Okay, so this motion is the way we have this motion now. It is counterclockwise. And counterclockwise motion is S. Okay? It is S. Now we also look at where the group of lowest priority is going. We see here the group of lowest priority is going away from us. So therefore, the assignment, the motion that we made in which it is counterclockwise, giving us the S configuration, will be correct. So therefore, the assignment, the configuration for this carbon here is S. And that is all they ask us to do. So therefore, I will simply now say the absolute configuration is S. That's all they ask us to do. Now, if you follow that, give me a happy face. Okay, very good, very good, very good. Okay, so let us go to the next one. Okay, on this next one here, okay, we all have agreed that we have only one chirality carbon, and that this is the chirality carbon. Okay, so what do I want to do? I want to also position myself so I could see this molecule, the chirality carbon, so that two groups that are coming at me in an horizontal fashion will be coming, those groups will be coming at me, and then two groups will be going away from me in a vertical fashion. So that is what I want to do now. So how do I position myself? Okay, you guys need to excuse my artwork. I'm not a good artist. So I will simply say, I want to lie right here. I want to stay right here. Okay, this is my leg here. This here is my right hand. And this here is my left hand. So, and of course, this is my head. Okay, I am laying down flat, looking at this carbon here, this chirality carbon. If I do that, now what I want to do now is to now write this chirality carbon in a Fisher projection. Keep in mind, our focus is on the chirality carbon, because all they ask us to do is to determine the absolute configuration of that carbon. So I will say, okay, that carbon therefore is this. Okay, the question I have for you, by the way, this is nitrogen, this hydrogen, hydrogen. The question that I have for you is, what group is going to be on my right? Valerie, I see that. Very good. Okay, NH2, NH2. Okay, very good. Now, what group will be on my left? What group will be on my carboxyl? Excellent. I think you guys are getting the idea now. Okay, so now you have this. And now what group will be on top of me? Or what atom will be hydrogen? And then below would simply be the CH2 that is attached to sulfur. And then, of course, sulfur is attached to hydrogen. Okay. Just a minute, I will be right with you. Somebody is knocking at my door. Okay, sorry folks, somebody was knocking at my door. Okay, I'm back now. Okay, so we are now. So what we want to do now, we want to assign the priority for to the groups. So which is priority A? Which is priority A? Exactly, the amino group. Great, excellent. This is A. Let me change the color of my pen. Which is priority B? Priority B, carboxyl. Excellent. Okay, of course. Oh, wait a minute. Okay, that is, I didn't see the sulfur. I'm going to take this back. This is not priority B. Notice what we have here. This carbon here is attached to this carbon, and then this carbon is attached to sulfur. Sulfur has priority over oxygen. Keep in mind the atomic number of sulfur is 16, whereas the atomic number of oxygen is 8. So therefore, this group here has priority. This group right here will be priority B. Okay? So make that correction, please. Okay, so that is B. Okay, and therefore the carboxyl is going to be C. Okay, somebody wants to ask me a question. Go ahead. Yeah, pick up the mic.
Okay, so my question is that do we automatically ignore the hydrogens when it comes to this thing, and we only think about the I guess.
Well, you just go ahead and you do not. What do you? No. Okay. I mean the hydrogen here.
Yeah.
Okay. Keep in mind. Okay. Keep in mind what we have here. Let me draw it better. Okay. I see your question. Very good question. Let me take this out. Okay. This is what we have here. The hydrogen is here. This is here. and then the sulfur is attached to the carbon. Okay, so the way you look at it is, okay, you say, okay, let us look at this carbon here, which is attached to oxygen. Then we also want to look at this carbon here, which is attached to sulfur. Okay, so you think of the sulfur first before you think of the hydrogen. In other words, you take a look at the atom that has the greater atomic number. So in this case, the carbon sulfur has a better chance than the carbon oxygen. And that is why we assign this group the priority B. Okay? And that is why we say this is priority B. I hope that is clear to you. Okay. So that is B. And therefore, this is C, and the hydrogen, of course, is D. Now we want to make our motion. So we make our motion from A. We go through B. And then C. Okay. What is that motion? That motion is clockwise motion. So that's a clockwise motion, which will be R. Now, once you do that, then you ask yourself, where is the group of lowest priority pointing to? In this case, it is going away from us. So therefore, this R is correct. Okay? This R is correct. So therefore, we come back here and say the absolute configuration here is R. Okay? Okay, is that clear to all of you? Okay, very good. Yes, very good, very good. Okay, so now let us go to the next one. We are going to get out of here by 9 because we are going to get out of here by 9 because I do want to respect all of your time. Okay, now let us see here. Kiera, can you go ahead and read this for us?
Determine if these molecules are methyl compounds.
Okay, determine if these molecules are methyl compounds. Okay, they want us to see whether they are methyl compound. Now, what is a methyl compound? Let us define a methyl compound. Methyl compound a methyl compound is that molecule. A methyl compound is that molecule that contains two or more chirality center but will superimpose on its mirror image. On its mirror image. Okay, that is a methyl compound. Okay, so therefore, when we take a look at this molecule here, the first thing that we need to ask ourselves, how does it have chirality centers? Okay, so let me go ahead and number this carbon here. Say this is carbon 1. Let us say this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. So this is a cyclic molecule. So therefore, can anybody tell me how many chirality centers do we have in this molecule? If we have any at all. 2. Okay, where are the chirality centers? We are at the chirality center, carbon 1 and 2. Excellent. Okay. So this is what we have here. Let me write this out in this form. This is the molecule that we have. We have here, this methyl group is on one side of the ring. This is a 5-member ring. The methyl group is on one side of the ring. That means the hydrogen is going away from you. I'm sorry, that means the hydrogen is coming at you. This is this hydrogen here, okay, coming at you, and the metal is going away from you. And then this metal is on the other side. Okay, the metal is now also on the other side of the ring coming at you. And of course, that means that the hydrogen that is here is going away from you. Okay. That is the molecule they have given us. Okay, now what they want us to do now is to determine whether this molecule is a methyl. Now, what do we need to do in order for us to determine whether this molecule is a methyl? Kiera, do you have a question? Okay. Now the question is, what do we need to do in order to determine that this molecule is a methyl? Fisher projection. Okay. In this case, if we want to determine the absolute configuration of each of the carbons, then we could do the Fisher projection of those carbons. But in this case, we may want to look at the possibility of whether this molecule here, the mirror image, will superimpose on itself. Keep in mind that is the absolute requirement for whether a molecule is chiral or not. In other words, let us go ahead and do that now. Let me erase this. Let us draw the mirror image of this molecule and see whether it will superimpose on its mirror image. Keep in mind that's what we said here. Okay, it does have 2 chirality carbon. Will it superimpose on its mirror image? That is the question we want to ask ourselves, give an answer to at this point. So let us draw that molecule again. You say we have hydrogen going away from you, coming at us, and the metal is going away from us. And also we now have the metal here coming at us, and the hydrogen is going away from us. So what I want to do now, I want to draw the mirror image of that molecule. Okay, so once again we have metal is coming at you, and hydrogen, of course, going away from you. And here, on the other side, you have the hydrogen coming at you, and take that back. The hydrogen is going away from you. Oh no, I got it backwards. The hydrogen is coming at us. That is correct. And the metal is going away from you, from us. Okay. So these are the 2 mirror images. Now keep in mind what we want to now do is to determine whether these 2 mirror images will superimpose. Now, how do I do that? What do? I could decide to slide this here to here. If I slide it, follow me now. If I slide it, do they superimpose? Yes or no? on top of each other? No, they do not. On the other hand, I could also keep in mind when you have these molecules, you could slide the molecule on the plane of the paper. You could also rotate the molecule. You could also rotate the molecule in a 180-degree rotation on the plane of the paper. Keep in mind, when you do that, you do not move the molecule out of the paper. You simply rotate on the plane of the paper. And then once you do that, you could then slide. If we do that, do these two molecules, do they superimpose? Yes or no? No. Okay. Therefore, the answer to the question they ask us is, this molecule here is not a meso molecule. That is the answer the question they ask you. Is this molecule a meso molecule? And the answer here is no. Now, I have given you one way in which you determine whether a molecule is a meso molecule or not, and that is by simply drawing the two mirror images and then determine whether they will superimpose. Let me also give you another way of doing this. And that was the way one of you simply told us that we need to do the absolute configuration by doing the Fisher projection. Okay, so let us try another way. But before we do that, let me start with a fairly simple molecule before we come to this one here. Supposing I give you this molecule here, or is it meso if it superimposes on both? Yeah, it is meso if both of the mirror images superimpose on each other. Yes, it will be a meso if both of the mirror images superimpose on each other. Now, supposing I give you this molecule here. Supposing I give you that molecule, of course, if you draw the mirror image, you will know very easily that the mirror images will superimpose. You will know that very easily. If I draw the mirror image, these two molecules here are mirror images. As you can see, if I rotate this 180 degrees and then slide it, they will superimpose on each other. Okay, but this is another way in which I want to show you without having to do the mirror image. If you have a structure, if you are given a structure, somebody is asking a question, how come all the molecules don't reflect? Or does the CA3 not matter, since it's one thing? I don't quite understand that. Basically, that means it's upside down. How come all the molecules? Okay, let me think about that question because I'm not sure I get the question at this point. Okay, so if you take a look at this molecule here, if I ask you, is this molecule a meso molecule? One thing that you could do, determine the absolute configuration of each one of the chirality center. If this absolute configuration, for example, if we do this, let us do the absolute configuration here. Let us focus on this carbon here. This is priority A. For that carbon, this group is priority B. And this is priority C, and of course hydrogen is priority D for that carbon. Okay? Now, if I make my motion from A, go through B to C, that would look like this. And that motion is a clockwise motion, which you will say that the absolute configuration should be R. However, because this hydrogen here, the group of lowest priority, is coming at us, in other words, it is in the horizontal position of a Fisher projection, meaning that it is coming at us. So this R, therefore, becomes S. Okay? So therefore, take this out. So therefore, the absolute configuration of this carbon here is S. This is S. Okay, no, use a different color. This is S. Okay? You follow that. Okay, if you follow that, give me a happy face. Okay, now, let us now come to this carbon here. Let us do the same, let us determine the absolute configuration of this carbon here. Does anybody know what the absolute configuration of this carbon will be? Let us make our assignment. This is A, based on this carbon here. This is priority A. How did you name the groups for the molecule? No, you did not have to name the groups in the molecule at this point. All you need to do is determine the absolute configuration of the chirality carbon. So anyway, so this priority A, and then this group here will be priority B. Keep in mind, our focus now is on this carbon. Okay, therefore, this is priority C, and the hydrogen is priority D. So once again, we make our motion. We make our motion from A. We go through B. We ignore group D. A to B. And to C, we ignore group D. If you look at that motion, according to what we have there, it is a counterclockwise motion. So you expect that it should be S. However, because this hydrogen here is coming at us, it is in a horizontal position of a Fisher projection. It is coming at us, so therefore we have to shift. We have to change the configuration to R. Okay, I see all of you already got that. That is excellent. So all of you guys already got that correct. So what am I getting at here? So we now say this is R. We say this is R. And we know that this is S. So now, if I give you a molecule and I tell you to determine whether the molecule is a mesomolecule or not, what to do, take a look at the chirality carbon. If you look at each one of those chirality carbons, you ask yourself, each one of them are attached to the same groups. In other words, this carbon is attached to bromine, attached to methyl, attached to hydrogen. The same thing on this carbon, attached to bromine, attached to methyl, attached to hydrogen. So both of the carbons are attached to the same groups or atom. Now, if the absolute configuration of each one of those chirality carbon is opposite, then that molecule is a mesomolecule. Okay, keep that in mind. That is very important. In other words, if you determine the absolute configuration of the chirality carbon and they are opposite, in this case, one is R and the other is S, or vice versa, then you know that you have a meso molecule, provided that each chirality carbon is attached to the same groups or atom. Is that clear? If it is clear to you, give me a happy face. Okay, so you can use that to determine whether a molecule is a meso molecule or not a meso molecule. Okay, so that is the second means of determining whether a molecule is meso. The first one is to see whether the molecule will superimpose on its mirror image. Sometimes that may not be that obvious. Therefore, it is sometimes possible for you to simply determine the absolute configuration of the chirality carbon. If they are opposite, then the molecule will be meso, provided the chirality carbons are attached to the same groups or atoms. There is a third way in which you could determine whether a molecule is meso. And what is that? That is much easier to do. You take a look at the molecule. I'm also going to admit that that is not always possible. Take a look at the molecule. For example, this molecule here, if I can draw a plane of symmetry, look at this here, what I call plane of symmetry. Okay, if I can draw a plane of symmetry in that molecule such that you have one group, the same group is on one side as on the other side, and if that molecule also have at least two chirality carbon, then you know you have a meso molecule. Okay, so so far I have given you three ways in which to determine whether a molecule is a meso molecule or not. In this case, this is your plane of symmetry. Look at this here, right here. It's almost like mirror image. You see, what you have on top is what you have at the bottom. In that case, that molecule will be a mirror image. The same thing happens to right here. You see? Okay? So those are the three ways in which you could determine whether a molecule is a meso molecule. Having said that, let us now go to the next problem. Unless you guys have a question. Okay. Okay. Now, what I've just told you now in terms of meso, we are going to use that in this particular problem here. This problem here is also asking us whether this molecule is a meso molecule. It is asking us whether this molecule is a meso molecule. Okay. So now, let us do this. I'm going to go ahead and number this carbon here. I'll say carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Can anybody tell me how many chirality carbons do we have in this molecule? And whatever it, okay, you say 2. 2 is correct. Excellent. Okay, which are those two? Give me the numbers. Which are the two chirality carbons? 3 and 4. 3 and 4. Excellent. That is correct. So let us go ahead and remove these other ones here. Okay? So carbons 3 and 4 are the chirality carbons. So you guys got that right. So that is the beginning of being able to solve this problem. Now, if we say 3 and 4 is the chirality carbon, the question is this molecule a meso molecule? This molecule is too big for us to be trying to draw whether it will superimpose on its mirror image. So which one of those systems that I gave you for the determination of meso, which one do you want to use at this point? Okay, keep in mind here, okay, plane of symmetry, okay, plane of symmetry, oh no, that could be difficult. The plane of symmetry is difficult because The way this molecule is written, look at here. The way this molecule is written, you have this group here is coming at you. This hydrogen and this hydroxy coming at you. On the other hand, this hydroxy and this hydrogen are going away from you. So it might be difficult to use that. So at this point, what I would advise for you to use the absolute configuration. Determine the absolute configuration. Keeping in mind, look at what they are. Carbon number 4 is attached to hydroxyl, attached to hydrogen, and also attached to a CH2, which is attached to a carboxyl group. Now take a look at carbon number 3, also attached to hydrogen, hydroxyl, and a CH2 attached to a carboxyl. So the chances are this could be a mesomolecule, but how do you determine that? You determine that by the determination of the chirality, the absolute configuration of carbon 3 and carbon 4. So let us do that. Let us determine the absolute configuration of carbon 3 and 4. So once again, I'm going to draw myself. I will use Miss Howard here to just, I'm focusing on this carbon here, carbon number 3. I am going to now have Miss Howard is laying right here. The leg is here. The right hand is here. I will say RH. The left hand is here. So she is laying down flat. Okay, my head is here. Okay, between Miss Howard and I, we are competing for this position. My head is here. So what do we have? Let us now represent this carbon here in a Fisher projection. Okay? That's just that carbon alone at this point. So we have that carbon is there. What is on my right? Can you tell me what is on my right? Hydrogen. Very good. Hydrogen is on the right. Can you tell me what is on the left? OH, hydroxy group. Excellent. You guys, I think you guys got this down to a science. Now, can you tell me now what is on top of me? That would be this CH2 with this carboxy group. Okay, very good. Okay, so at this point, I am simply focusing on the this carbon right here. So therefore, the group below me will be this here, this carbon here that is attached to hydrogen. We don't have to draw all of that out at this point. All we simply want to do here okay, keep in mind our focus is on this carbon. We are not focusing on this carbon yet. Okay, so therefore, let us go ahead and make the assignment. What is priority A? What is priority A? Exactly, hydroxyl. What is priority B? What is priority B? Okay, this group here, carbon attached to oxygen. Okay, this is priority B. Okay, therefore this will be priority C, and hydrogen is priority D. Okay, so now we want to make our motion. We want to make our motion, okay, from A, we go through B to C, ignore group D, so we have this. That motion is counterclockwise, so that means that should be S. However, because the group of lowest priority is coming at us, it is in the horizontal position of a Fisher projection, so therefore we are going to say that that is actually R. Okay? Do you follow that? Okay, very good. Okay, so therefore, let me take this out. Let me take all of this out. This out. So we say this is R. Okay, now we want to focus on this carbon. We now want to focus on, let me take this one out here. Okay, keep in mind the most important thing that you want to do is to position yourself so that you see two groups in the horizontal position of a fissure coming at you, and therefore the other two groups will be going away from you in a vertical position. Okay, so those of you who do not understand this, please see me in my office tomorrow. Okay, so therefore, if you do that, let me now do my Miss Howard again. So what I want to do, at this point, I am focusing on this carbon right here. If I focus on that carbon, look at what is happening. This group is coming at me. This group is coming at me. The OH hydroxy group is going away. Hydrogen is going away. So I'm going to lie right here. I'm going to lay right here. My leg here. Okay, my head is here. My right hand is here. RH, my right hand is here. And my left hand is here. So in other words, I am laying flat, looking directly at this chirality carbon. Okay? Okay, if that is the case, let us now take a look at this carbon. I'm now focusing on this carbon. I want to focus on that carbon now, so I say, keep in mind, we already said that, let me do this. We say that this carbon here is R, so don't let us miss this. We say this is R. So I take all of this out. Our focus now is on this carbon. Keep in mind, you focus on one carbon at a time, and then you position yourself such that two groups will be coming at you. Once two groups are coming at you, then the other two groups will be going away from you in a vertical position. The two groups that should be coming at you should be coming at you in an horizontal position. And that is what I've done here. That's what I've done here. Okay, so let us now say that carbon number 4, is this here. What is on top of me? Let us start with that first. What is on top of me? OH, excellent. OH is on top of me. Okay, you guys got that right. OH is on top of me. Below me, what is below me? Hydrogen. See, once you position yourself right, everything would simply fall in place. Now, what is to my right? What is to my right is this group, right? Okay, that is CH2 with the carboxy group. And what is to my left? You have this group here is to my left. Okay, very good. So that is, this group is CH attached to hydroxyl, and then attached to CH2, then attached to carboxyl. That is what's on my left. Now, let us now make our motion. Let us now make our motion. Oh, I'm sorry, let us do the assignment first. What is priority A? OH. What is priority B? Of course, this group here, because this carbon oxygen here will have priority over carbon. Okay, so that is B. And then this is group C, and this is group D. Okay? We go by, why is OH always priority A? It isn't always priority A. We go by the we go by the atomic number of the atom. Oxygen has an atomic number of 8, and of course you know that carbon has an atomic number of 6. So that is why oxygen always has priority over carbon. Okay. So now, what do? We make our motion. We make our motion from A. We go through B to C. We ignore group D. And that motion, right now, that motion is counterclockwise, and therefore that is S. And then we look at the group of lowest priority. So the group of lowest priority here is going away from us because it is in the vertical position of a Fisher projection. Okay, so therefore it is actually S. So we keep the S. So what we have, we say this group here, this here has an absolute configuration of S. Okay, remember what I told you in the previous problem? See what they are? One is R, one is S. Okay, therefore, this molecule is a meso molecule because you have the chirality carbon. These two chirality carbons have opposite absolute configuration, and also because each one of these carbon here is attached to the same groups or atoms. Keep that in mind. Each one of these carbon is attached to the same groups or atoms. Okay, is that clear to you? Do you have a question before we go to the next problem? So this question, therefore, yes. Go ahead and ask your question. Somebody wants to ask me a question. Go ahead.
When you are trying to use the planar symmetry method or whatever, are you saying that we can only use it with the taking into consideration like the wedge and dotted line method or whatever? Or because if you just use the Lewis-Fisher whatever thing that's called.
Yeah, I get your question. Very good question. Yeah, I get, I got your question. That's an excellent question. The reason why at this point you could have used the plane of symmetry method, but the way this molecule is written, you will have to do something else to this molecule in order for you to see that plane of symmetry. And I will show you that in class tomorrow. I do not want to confuse people by using that method on this molecule at this point. But yes, if we do whatever we are going to do tomorrow to manipulate this molecule, yes, we could use the plane of symmetry. But for now, don't let us use the plane of symmetry. That would not be appropriate for this time, based on what we know at this moment. Yeah, go ahead. Somebody else ask a question.
So you can only use the R and S rule for when they're attached to the same groups?
Yes. That is the only way they can be meso. Because if they are not attached to the same group, they can never be meso molecules. Okay? Okay, so oh wow, time is gone. We have 8:59. Just lost me. Okay. Tomorrow we will go over the meso again, but I thought we could do. I didn't know the time has gone so fast. Okay, well you guys can do this. This is simply saying assign R and S configuration to the chirality centers in this molecule. Of course, this molecule here has this chirality center here, and also has this chirality center here. So you guys should be able to do this. I'm going to leave this for you to do. I will just give you a hint when you do this. You want to position yourself. We say Miss Howard is sitting right here, that the head is here, and the leg is here, and the left hand is here, and the right hand is here. So she's laying down, or I am laying down, whether it is me doing this or Miss Howard, it doesn't really matter. That is the way you look at this here. Because this group is coming at you in an horizontal fashion, and this other group is also coming at you in an horizontal fashion. Okay, so that's the way you do that. Then when you then come to this other chirality carbon here, the way you look at that is to look at this here. You should lay right here. The head is here, leg here, leg here. This is the right hand, and this is the left hand. Okay, that is the way you look at it. In that case, when you draw the facial projection, this will be on your right and this will be on your left. So I just thought I should give you a hint on how to do that. And finally, let us do, okay, let me see. Ines, can you go ahead and read this for us before we leave?
Draw a carboxylic acid with the formula C5H10O2.
Okay, very good, and thank you. I thought we should end the session today with a very simple problem. They want you to use this formula here to draw a chiral carboxylic acid. Now, what do we mean by chiral? What do we mean by chiral? Anybody know what do we mean by chiral? Okay, well, excellent. A molecule that does not superimpose on its mirror image. We say that's a chiral molecule. So therefore, we want to draw any carboxylic acid. So let us say we have carboxylic acid, carboxyl group. As long as it is a chiral molecule, you could use anything, any molecule that you have here. You could say this. As long as you use the formula they gave you. Okay, so how many carbons have we used? 1, 2, 3. 2 more carbons to use. Okay, does this formula fit what they are giving us? We have 5 carbons, and how many hydrogens? 5, 4. Yeah, 5 hydrogen and 2 oxygen. So this formula fit, this structure fit this formula they've given us. Okay, based on this molecule that I've given here, you remember I told you, anytime you have a molecule that only has one chirality carbon, that molecule will be chiral. Okay, keep that in mind. Any molecule with only one chirality carbon will always be chiral. Any molecule with only one chirality carbon or center will always be chiral. In other words, that molecule will not superimpose on its mirror image. So if you draw the mirror image here, you will find that the mirror image of this molecule will not superimpose on itself. Folks, you could actually draw as many different structures as you want, as long as they meet the requirement of the molecule being chiral, and the molecule must be a carboxylic acid, and it also have this formula here. So at this point, we have come to the end of our session. I will stay around for another 5 minutes in case some of you want to ask additional questions. In the meantime, I am going to turn off the recorder, so the class is the review session is officially over once I do that. Okay, so let me turn this off. So until I see you tomorrow, enjoy the rest of your evening.